All right, welcome guys. Welcome to the DSP101 first lecture. Here is going to be our curriculum for our course of DSP101. We're going to have a lecture a week, and we're aiming for, in this course, I don't know why I'm saying we, it's just me. I'm aiming for like 4 or 5, but that 5th one is like TBD. It's like an advanced concepts one, which I might cover if I think it's going to be like useful, but we'll see. So this is our curriculum. Today we're going to cover, like I said in the title, DSP and communications basics. Just as a show of, like, could you tell me guys what year you guys are in and if you've taken communications classes before? So Matthew.
Yeah, I'm gonna go into second year.
Okay.
I haven't taken
No.
my courses really.
Got it. What's your name?
Brendan.
Brendan.
I'm going to second year, and I'm an art science student,
So no.
I don't have that.
Okay, I'm just trying to gauge everyone's background. Shupong, you've taken communications class before? No? Oh, okay, got it. And then your name? Hasiba? No? Got it.
I'm not sure what the communication course.
So have you covered things like analog modulation, AM, FM? No? Okay.
Just finished third year.
Oh, yes, you told me about that one. Okay, so now I know the kind of background level. So today,
No, me, bro.
I have you?
I've done some like math, like 4-year transfer, but not application.
You haven't done a communications class?
I've done like 4-year transfers and stuff like that.
Okay.
It's not like application.
Oh, okay. Got it. Okay. So yeah, I'll keep that in mind. So yeah, today we're covering DSP and communications basics. We're going to cover an overview of these things, the tools that we use, that we'll use in the RF comms team and the DSP side of it. We'll cover things like sampling, Nyquist limit, and then some basics of different modulation schemes, which this all might sound Greek, but it'll hopefully make a lot more sense by the end of today. Then we'll progress on to, I ignore the fancy terms. I'm just going to go then. This is the introduction today, and then I'm going to go digital communications is the rest. So we're not going to cover digital communications today, which is basically the systems that we have in the world, transmitting bits, which are everywhere, your phone, your laptop, everything is digital nowadays. It's a lot more complicated, so we'll devote multiple lectures to it, but we will get to that, and then at the end, some advanced concepts. So without further ado, let's begin. So we don't have a huge communications background here today, but that's okay because we'll cover it just really straightforward and really simply. So communications, the role of signals in communications and modulation hierarchies. So first of all, introduction to communications. What are we talking about when we say communications? This might be really basic, but bear with me. So the goal is, right, send information from point A to point B. Simple enough, right? Okay. So the question is then, how do we do this in practice? How does Wi-Fi work? How does, when you text your friend, how does that information get sent from A to B? Well, the answer is all about signals. So the way it works is some clever people a long time ago realized that if you took a signal and you vary it in a specific way, you can transmit information. And this isn't a new concept. Think of your friend in like across the street from their window at night, let's say hypothetical, and they have a flashlight and they're shining on and off from Morse code. We've seen that before. Like that's a thing that you can do to transmit information. The same thing is true here with signals. So like I said, you could encode information into variations of a signal, and that's how communications works, right? So if you look at this picture down here, think of the flashlight example. You could see it as Morse code, but you also see it as yes or no's. Like yes is on, off is no, and then therefore you transmitted information just by varying a signal. So that's kind of how that works, right? Now, when I say varying a signal, what do I mean? Well, in all of communications, we always mean a cosine because it's smooth, it's predictable, it's our go-to, right? So we have a sine wave, a cosine. I say sine or cosine interchangeably. I mean the same thing. So you have a cosine wave, it's oscillating. And what you can do is you can then vary that cosine to transmit information. And there's 3 ways you could transmit information. Depends on how you want to do it. They're all kind of equally valid ways. And they are, you can change the amplitude of that cosine wave, the frequency, or the phase. So let me give you an example. Let's say that I told you, hey, I'm going to go really far away and I'm going to go check on something and I'll tell you yes or no if it worked. Then I could send you back a cosine wave and a high amplitude is yes and a low amplitude is no. So I just transmitted information. I could do it with frequency. High frequency is yes, high frequency, low frequency is no. Or I could do it with phase, which is like, how much it's cosine or sine. I'm sure you guys heard of phase before, but so those are the three properties that we can vary. Now, what I just described is something called modulation. It's the process of varying a signal to encode information. That's what modulation is. You might have heard that word. AM, FM in your car radio, right? Amplitude modulation. We're varying a signal, its amplitude to encode information. FM, we're varying the frequency, like I said, to encode information. So that's kind of the basics of communication. It all comes down to modulation. That is the trick that some clever people a long time ago came up with. So I have a diagram here showing there's kind of two types of modulation. And we're going to focus today on the kind of the analog, I guess, briefly. And project 1 covers analog modulation. But so modulation, as I said, is varying a wave to encode information. Now, you can do that. There's something called digital modulation, analog modulation. And we'll cover what these are a lot more later down the line. But for now, I just want you to know that these types exist. And there's these terms you've heard before, maybe in your car radio, AM, FM, PM. That's analog modulation. That's all analog. So that's old-fashioned stuff. When you guys hear analog, you should think like your parents, like their parents. Like that is super old nowadays. It's all digital nowadays. So nowadays, we don't have AM. We have something called ASK and FSK instead of FM. So it's all kind of changed. Maybe rarely, sometimes you might see AM or FM, but yeah, it's all digital nowadays. So I mentioned that modulation, you have a cosine, and you're like, how do I vary that? You could vary the amplitude, phase, or frequency to encode information. Well, we know, hopefully you guys know from basic kind of math, that a sine wave has a frequency associated with it, right? Now the question arises, well, okay, I mentioned frequency modulation, but if we forget about that for now, let's think of amplitude modulation. So we have a cosine, and we want to vary that to convey some information. So I could ask you, what frequency do you want to put for your wave? Well, that's an interesting question because I don't know. Does it matter? Does it really matter? Well, yes, actually it does. So the reason why it matters is there's 4 reasons. I'll start with the most important one, which is antenna size. Shout out Juno over here, lead of the antenna kind of course. So there's a link between frequency and antenna size that you need, in the sense that let's think of baseball. You have a ball and you have a glove. If the frequency was the size of the ball, to catch a really big ball, you need a really big glove. And to catch a small one, I guess let's say you have to have a proportionally small kind of glove to catch it. So the idea is kind of the same here. The larger the frequency, the larger the antenna that you kind of need to capture it. Actually, it's the inverse relationship. It doesn't, but the principle is the same, right? Like there's a relationship between them. So this is what we're seeing here. So this is actually a car antenna. It's on the top of a car. You've definitely seen that before. So that's actually an antenna. And you can see the size difference, and that all comes down to frequency. This is, very low frequencies, and this is very much higher. And it can get like in your phone, there's little antennas that are even higher frequencies. So that's one reason why the frequency matters and what influences it. So then, cost, all these different things, right? Regulations, what bands you're allowed to use. Guys might not have heard of this, but there's a government agency that regulates like frequency use. Wi-Fi is this to this. Bluetooth is this to this. So you have to adhere to that rule. And there's a military band. Wouldn't want to be transmitting over like sensitive bands that could be, or there's an emergency band. Like, you have to stay out of certain zones. So regulation influences what frequency carrier we use. Then we've got propagation characteristics. This comes down to physics. The atmosphere might block a certain frequency but allow another to pass. That matters. Bandwidth. This is just because lower frequencies have been more popular, so a bunch of people have used them up. But higher frequencies, which are a bit harder to kind of use, are mostly empty. So that one is a bit more free. So bandwidth, which we'll cover what that means later on, but more space available. So anyway, I just want to emphasize the point that frequency to use is based on many different things. And these are kind of the main ones to keep in mind. Okay, so let's cover amplitude modulation because it's the simplest way of doing communication. Just to remind you guys, we have the modulation diagram here. We're now considering analog modulation, and what? Okay, don't worry about that. We're considering analog modulation, and we're doing AM now. So it's on that right branch. So what is amplitude modulation? So the idea is, don't ignore these blocks for now. Just look at this diagram with me. So this is our message signal. I know it's a cosine, which might be a little bit confusing, but let's just say that we want to transmit. I want to transmit this information. You know, I want to talk to Juno and I want to send him this wave, and he wants to receive it. So what we do is with AM, we vary. Remember, it's all about varying a carrier. So here's our carrier, and we're going to vary this carrier according to our message. And what you can see here is now I've taken this and I'm varying it according to the message signal, and now it's kind of encoded into it. It's baked in a way, right? So now if Juno could receive this, discard the carrier and get back to this. So that's kind of amplitude modulation. You can see the envelope here is reflecting of the message signal. So just some terms to keep in mind, message signal and carrier signal. So think of it like your envelope is the carrier, because it just carries your message from A to B, and well, the message is the contents of the envelope, right? So that's all the carrier does, just carries it, right? Yeah.
Is the carrier wave and the wave, are they being added or are they being multiplied?
Good question. So here, actually, you can think of it mathematically. How we do modulation is actually, in this case, a multiplication. It's that simple. Like, you might be like, what? But if you actually did it, even on Desmos, like if whatever, right? If you made two cosines, you draw them individually, whatever, plot them, and then actually you plot the product, you multiply them, you'll get this. And that's actually how you encoded the information, the message, onto your carrier. So that's why I'm covering amplitude modulation. It is super simple. If you wanted to make an AM transmitter, all you have to do is take your message signal, take your carrier, multiply block. That's it. And then you have a transmitted signal, and then you're good to go, right? Yeah. You might be wondering why we wouldn't just transmit this individually. It's because, like I mentioned, frequencies matter. Like, this is a low frequency, and maybe you want to go to a certain frequency. Let's say you want to go to like a gigahertz. You could then go to a gigahertz by using a carrier at a gigahertz. So it's like how you get to different frequencies. Anyway, so that is kind of communications. And also interrupt me if you guys have any questions. I want to keep this kind of like informal, right? So that is the basics of communication. Hopefully that makes a little bit more sense of kind of what we're doing here in this field using signals. What is modulation? You know, varying a carrier according to encodes information, and importance frequencies, and then AM. So AM is going to come in handy when you look at the onboarding project 1. I'm going to ask you to make an AM system, and you'll just literally, I'm giving you a hint, but you'll just put a multiply block because it's that simple. Okay, tools. So we're going to cover something called an SDR, or SDRs, and GNU Radio. So have you guys heard of these things before? Yeah? Anyone used GNU Radio? You've messed around with it a little bit? Okay. So I'll first cover what the hell are software-defined radios. So I have one with me, so you can get a sense immediately for what I'm talking about. It's in the picture too. What do we see here? So first we see a USB stick, we see an antenna, and we see a block. Now, this will plug in your laptop. That's the first thing. And now let me explain what it does. So now that's what it is. Now, what does it do? So here's some history for you. If you wanted to build a communication system, let's say you wanted to build a transmit. When I say system, I mean a transmitter and a receiver. So let's say you wanted to build a transmitter to send a message to a friend of yours. The old-fashioned way, back in our parents' age in the 90s or whatever, 80s, actually even before then, what you would do is you would have a bunch of these big hardware blocks. Like, this is the modulator, and this next step is what's going to turn, I don't know, bits into something. And they were all very physical analog devices, very big, bulky, and they were like hardware essentially, right? So SDRs are a game-breaking, game-changing kind of innovation in the sense that it shifts all that communication system logic to software. So I can design a transmitter and a receiver all on my computer. So without it, we wouldn't have a club here, because, I mean, we would, but it'd be very different. We'd be in the lab here connecting wires and looking at scopes and things like that. But instead, we can design a whole system on our computer. We can receive a signal, and then I can process it on my computer, all in software. So that's all it is. It's just making a communication system in software. That's how you think of a software-defined radio. I like this quote: thousands of dollars in equipment reduced to $20 to $50 because the computer does all the work. This is what I found online. Some like old guy was saying this in like some YouTube comment. But like, you can see how amazing this invention was, that you can your computer can do everything. I've included this. This is a block from GNU Radio, which I'll cover in a sec. It shows this is how you would instantiate your SDR. It's that simple. You'd go, okay, I want a Pluto, which is a type of SDR source. And then this out port would be where your like information comes out of. And there's just two parameters. You can set the center frequency, the carrier frequency, and this thing called sample rate. And I just wanted to show you guys that this whole hardware just becomes a block in GNU Radio. It's that simple. And there's only two parameters. So this thing is doing all the magic for us, and you just do everything on your computer. It's really easy. So here is GNU Radio. This is the environment that you'll be working with, presumably. This would be your SDR block, like I just mentioned, and then boom, the rest of it is your communication system. So this is the block that I've been working on, a part of work here at UTAT. This was a digital communication like system. I've got a transmitter section here, then a receiver down here. Oh my God. So what do we have? What do we have here? So immediately we notice that everything is blocks, and that is kind of GNU Radio's MO. So it's a software tool for designing and simulating communication systems. It's flow graph based. So it's just dragging and dropping blocks, which is great. No code. There could be code because you can make custom blocks and define what they do. But for the most part, it's just adding and dropping blocks. It's really easy. Something about real time, yeah, process samples in real time, whatever. Python integration is what I'm saying. So it allows you to create custom blocks using Python code, which is really, really handy. So yeah, this is what we're working with. So for the first project, you'll get familiar with how to add blocks and connect them together and what the different colors mean. But it's really, really straightforward. Okay, so that's just the tools that we'll be working with. Yeah. Yeah. So, I've made a few. Tornava made one recently to calculate the bit error rate. So he you can define pretty complicated algorithms in Python and then just have them as a block and define the inputs and outputs, and it's really great. But yeah, we do use that all the time. Okay, so now for the most important section, and we're getting right into it. So the DSP basics. So given that you guys haven't really taken any communication systems classes before, I'm not going to assume you've done DSP. You might have done some signal stuff. You've done Fourier stuff. Who here knows the Fourier transforms? Few people? Okay. I see. So when I say, I'll just introduce DSP from the ground up. So when I say DSP, I mean digital signal processing. And basically what we're doing is, you know what? I'm going to pull up a picture. I should have put it, ignore that. I should have included it in my slides, but I'll show you guys. So this is what I mean by digital signal. So this is a good picture. So we have these things called analog signals, which analog you can just think of meaning continuous. Like this gray one, it means that it's defined at every point in time. It'd be like if you spoke into a microphone, there's no gaps in your speaking. It's just always defined and it's always ongoing. It's capturing your volume. And then what is a digital signal? Well, a digital signal is what you get if you sample. That's a key word, sample an analog signal. And this red chain of samples is a digital signal. That's all we mean by that. And the key here is that processing a continuously varying analog signal like this is impossible in a computer. Your computer, you guys might know, but it can only store certain numbers, and it has let's say this analog one is defined at 3.00001 and then 3.0. It's literally infinite resolution. It's defined at every single point between 0 and 1, but a computer doesn't have finite infinite memory. So it can only work in these red signals. And the whole idea here is we approximate the gray signal with the red one. If that sounds like a bit like what he's talking about, just keep in mind that computers only work with digital signals, and that we're approximating the gray one with these red ones. And the whole idea is to hopefully our approximation is good enough that it doesn't matter. It's literally seamless and it's the same thing. So that's the whole idea with DSP. And then let me make this full screen. Yeah.
So analog signals are continuous signals?
Yes.
Digital signals are discrete signals?
Essentially, yes.
Okay.
That's basically all there is to it. So then when I say DSP, I mean the processing involved acting on those digital signals. That's just like how we work with those digital signals and things that we do with them. So I have quite a big analogy here. I want you guys to bear with me. I don't know if it's going to be absolute crap, but I thought it was really good when I made it. Let's see. Okay. So now we understand, hope, like a little bit about like what it what an analog signal is and a digital signal. Okay. So when you have a computer, I told you only works with digital signals. I also told you that on GNU Radio, I can do all this processing and build a communication system and all this stuff, right? So I'm working on digital signals and I'm approximating analog ones. Okay. So here's how I want you to think about it. So imagine this is your computer, the city, okay? And this is, where is it here? This is like your, the real world is analog. All signals in the air are analog, but in your computer, they're digital. So this is your computer, and then here's the real world, and you've got your signals that go in, your analog signals coming here, and then this thing will turn them into digital signals. It samples them in this thing. And then the output of the USB part here is those digital signals, right? Now, here's the analogy, and here's an important thing to keep in mind. So I said earlier that we're approximating our analog signals with digital ones. Now, the hope is that approximation works. Like, what if it ruins it and we lose information? And that is a valid concern. And that's where this idea of something called the Nyquist limit comes in. Okay? So that gives us the limit to where this breaks down, where you can no longer make that approximation of an analog signal with a digital one. Now, here's why I like this analogy of the city being your computer, because if we look at the city here, our computer, we can see these gates, and these gates have a finite height. And that is expressing what I mean by a limit. Like this, it'll let in stuff from the outside world, and it can pass out, and it's the same person, whatever. But there is a notion of, okay, this approximation breaks down when people, let's say people that are too tall for the gate walk in, and it doesn't work. So that is the Nyquist limit, and it's really small here on my laptop here. But what I'm writing is F max, the limit, is Fs over 2. And what that means is I mentioned that with an analog signal, we make a digital one by sampling it. And therefore, there's something called a sampling rate, which is the rate at which you like produce those samples. And that's Fs, the sampling rate. And what I'm saying here is the maximum frequency that you can represent as a digital one without losing information is your sampling rate over 2. And if you are sampling a signal that has a higher frequency than that limit, you lose information. It doesn't work. So it's all about frequencies. Okay? I'm going to explain this again a few times with the analogy, but that's the initial idea. So now let me take this analogy further. So I want you to imagine people and their height being the frequency. So you have a bunch of people walking in, a really short person walks in, they get through the gate. It's awesome. They go around the city. We do some processing on them. Don't ask questions. Then they leave. Okay, and nothing happened. Like the gate never bothered them. The Nyquist limit never was a problem to them. But if someone walks in who's too tall for the gate, here's the tricky part. So you might think, oh, they can't get into the city, and that would be good because then we would just go, oh, like our system just doesn't work with those frequencies. Ah, damn. No, it's worse than that. If you were to go, let's say you really want to go in the city. There's something really cool in there. You wouldn't just stop. You would bend your knees and duck under the gate, wouldn't you? Because you want to go in. And that is the problem, because signals will come here of a high frequency. They get to the gate. Instead of stopping, they'll bend their knees and duck under the gate. And now they'll pretend like they're a short person. And that's called aliasing. It's great. Alias is in like taking another identity. And the problem is that your frequencies have changed and there's distortion and everything's messed up. So you lose that frequency. Let's say it was 300 kilohertz. Now it might look like 150. And that could be a big deal. Think of like our sound. When you speak, you make frequencies with your voice. That could distort the complete what words you're saying. It's all messed up because those frequencies have been removed. It doesn't work anymore. So that's this idea of the limit. So you have to bear in mind, okay, I'm capturing audio. If you guys might know, the audio is, I think, 20 to 20K, something like that, hertz. So if I have that in mind, okay, I want my F max, the height of the gate, to be like 20K, because that's 20K, 20 kilohertz. Okay. Yeah, I should be more precise. So I know that all of audio is 20 to 20K hertz. If I want to capture all possible, things someone could say, I should make sure my gate is tall enough. Because if it's 10K, my Nyquist limit, I'm going to lose high-pitched noises, and it's just going to be a bunch of low-pitched stuff, and my song is going to be messed up. Is that kind of making sense so far? Hopefully. Yeah.
Okay, so if the sampling rate is 10 gigahertz,
yes,
the maximum frequency that we can represent is 5 gigahertz.
Correct.
What if you want to represent 6 gigahertz? Is that when we can't even represent that? It will distort the signal.
So what would happen then is you have 10 as what you want to represent.
No, sorry, 5 gigahertz is what I want to represent. 10 gigahertz is like sampling.
Oh, okay, yeah. So your sampling rate is 10. So first, that means that the height, your Nyquist limit is fs/2, which is 5 gigahertz.
Right.
That's the height of your gates.
Right.
Okay, and you want to represent 6, you said, right?
Yeah.
Okay, so immediately it's not going to work, right? Like in the sense that 6 is not going to be able to pass through normally through your gate because the gate's at 5 and it's at 6. It's going to bend its knees, and it's going to now look like 3.
Right.
And now you've lost that frequency. It's different. And it's gonna, if there was existing 3, there might be, you said gigahertz, right?
Yeah.
If there was a 3 gigahertz component already passing through, the 6th one is gonna become 3 and now interfere with it and mess it up. So it just causes all kinds of problems.
Okay, so if it's 5 gigahertz is different.
Yeah. So
if we wanted 6 gigahertz, you would need something like 12 gigahertz or something.
exactly, you could increase the height of the gate if you want to capture higher frequencies, or you can do something else. I'll get to that in a sec. I have another slide about this. Sneaky visitors. So I was saying about physical signals taller than the gate. They perform a trick. They bend their knees to squeeze under. These tall intruders are like identical to legitimate shorter residences. So that's, yeah, the gates are crazy. So the next concept is protecting the system. So you mentioned one thing there about you could increase the height of the gate. But the problem is, let's say you want to capture 6 and you increase the height to 12, and that works. But there's always going to be higher frequencies. Like it can go on, like it could be 50 gigahertz, and those could fold down. They could bend their knees and interfere with your system. So you want to get rid of anything you don't need. You want to get rid of these tall guys. We don't like tall guys. Okay, we don't want them in our system. Okay, so this is the idea of this thing called the anti-aliasing filter. Think of it like a guard at the gate. It's going, hey, no bending your knees. You can't get in here. And then that's good because there's no corruption or interference anymore when they come in, right? So that's the anti-aliasing filter. And you won't have to worry about this in GNU Radio or any of your work because it's actually like taken care of in a lot of the blocks automatically. But it's just good to know, like, this is a thing. So yeah, the security guard station at the entrance of the DSP city. This is getting crazy. Okay. Yeah, the guard shears it off. God, that's dramatic. Before it ever reaches the city. Don't worry about the blue part. Okay, so here you gave an example already, but I had some here. So start with scenario A. So your sampling rate that you chose to use for your system is 32 kilohertz, and the signal that you want to capture is 10. So here the Nyquist limit is 32/2, which is 16. So clearly your signal is going to pass through just fine, and it won't get aliased down to a lower frequency. So yay, success. Scenario B, FS is 32, but now we have signal as 20 kilohertz. This is 20 is over 16. It's higher than 16. So this one's gonna, alias down to, it says 12 here is the answer. There's a way to calculate that, but it doesn't matter. But it's gonna bend its knee and become 12 now. So it's different, it's changed, which is not good. We don't want these things to change. Frequencies matter a lot, what they are. And if the frequencies of your signal change, the whole message is corrupted and everything's different all of the time, right? All right, so that's the idea of the basics. This is DSP basics. Like this is the key idea. You have the digital signals, and then you have this Nyquist limit, and you have sampling rate, and all this stuff. That is like the key idea, and it's so misunderstood. So I just really wanted to cover that today. So a little bit about the onboarding DSP project number 1. I've mentioned number 1 because there's going to be 2. The second one is going to be about digital communications, which will be. I was debating just doing 1, but I think that when I joined in January here at UTAT, and the first thing I did the first few months was just like build a digital communication system. It took me like two or 3 months, just because I was like getting used to everything. And when I built that, I felt like I was finally like ready to like, I don't know, help do progress and like make progress and stuff. So I think it's a good prereq to like really understand what's going on. So that's project 2. Project 1, what you're going to do is build your first ever communication system, which is going to be amplitude modulation. There's going to be 3 stages. So first is I want you to, the first stage is kind of boring, but you got to get through it. It's just build a system to transmit a sinusoid wave. So you're going to have a lower frequency wave you want to transmit your message and your carrier, and you're going to transmit that and then decode that receiver and then show me that you got that out. Second and third part are more fun. So I want you to pick a song, any song of your choosing. You can go on YouTube. There's the instructions in the project, but go to YouTube, pick a song that you want to transmit over your communication system, copy the link, and then you're going to actually show me that you can send your song from A to B. Like this is like sending a song to your friend who's really far away. And then part 3, I want you to mess it up. I want you to add noise to the channel, and I want to like I kind of want to have a competition for whenever you guys finish the project. I don't know when that deadline is, but you probably do it like as soon as you can. But I want to see who can mess up the song like the most. Actually, it probably wouldn't be very hard, but I want to see it from each of you, honestly. Like, here's the song, undistorted, beautiful, sounds great at the receiver. Here's it a little bit more messed up. Here's it like super messed up. And it'll be kind of fun to like see how like messed up you can make your favorite song just with like noise and stuff, which simulates, it should show you like the challenges involved and like honestly what to expect. Like a lot of the time it's going to be messed up and you have to like fix it. All right. Yeah. So that's all we had for DSP 101 lecture 1. We'll do any questions about stuff we cover. I can go back and like look at the slides.
I was kind of wondering about that anti-aliasing thing.
Yeah.
So does that happen before the signal gets sampled or after?
I explained it in the sense that it would happen after, but that's technically incorrect. But the concept, so I had it here in the blue. Technically, this is an analog filter placed before the sampler. That's the truth of the situation. There's reasons for that. Because I forget, it's been a while since I've done it.
Sense because like
conceptually,
if it's after it gets sampled, then there's no way to even know which one, like which signals are beyond the limit, right? Is it?
No, if you design your filter correctly, essentially the way you design your anti-aliasing filter is you know what frequencies you're interested in. Like if I only care about up to 20 kilohertz, I'm going to design my anti-aliasing filter to have a cutoff at 20. So you could, I see your point, but it's not technically true. You could do it in digital. I think the reason why, I might be wrong, but I'm pretty sure I remember that it comes down to like cost or like physical hardware. Sometimes I think things that might be easier to do in analog. I don't know, but that's a more of an implementation detail, but the idea is the same, that like they're protecting your signal from higher frequencies. And don't get too tripped up about where it is, but if it's before or after the sampler. But if you want to look that up later, let me know what you find. I'll be curious. Yeah, any more questions? No, FS is the sampling rate. So F max is the limit. Think of it like the height of the gate. So F max is then called the Nyquist limit. Sorry.
Like the max frequency.
Yeah, I've written. It's a bit confusing because I should have wrote like FN instead of F max because it makes you think that like you're thinking about the maximum frequency of your signal that you care about. Like, kind of, not really. Instead you think about like FS sampling rate over 2 is the Nyquist limit, and call it FN. That's better because then you could have FN be more than F max as your maximum frequency. You just have a bit of guard band. Any more questions? Yeah.
So the population, you're multiplying the message signal and the carrier signal, right?
Yeah.
What does that mean hardware? Like what hardware is there?
So there is something you can do it in analog. There's an analog circuits class you can probably take at U of T that goes in details of how you make a multiplier block in analog hardware. It's a thing you can make, but the technical term for a multiplier is called a mixer. Oh my God, not that, not that kind of mixer. I don't think people on the recording will be able to see me sharing these. I didn't do it too much. It's okay. But yeah, when I say a mixer in communications, this means the multiplier. So like here, input signal, your message, and that means the carrier, and then you've got your output. So mixer. Share this data set. There you All right. Okay. I think that's all the questions we had. So yeah, I've released the project one. Let me know if you have any questions about it. There's no like hard deadline on when to do it, but we're going to move on to digital communications next week. So we'll move on to new things. So, I mean, I would advise like try and do it the next week, but it shouldn't take too long. But like, don't stress. Don't stress. Just you should like take your time with it and enjoy it if you can. Yeah. All right.